All right, welcome back, focused learners, to another explainer. We've got a truly fascinating mission today. We're going on a deep dive into a groundbreaking collaborative paper from researchers at DeepMind, Google Brain, and MIT. The paper is called Relational Inductive Biases, Deep Learning, and Graph Networks, and it tackles what is arguably one of the most profound challenges in artificial intelligence right now: unlocking true, human-like reasoning in machines. It's kind of crazy when you think about it, right? I mean, pose this question to yourself for a second. Why is it that a human baby can generalize concepts about the physical world better than a state-of-the-art supercomputer? We are living through a massive computational renaissance. AI can translate languages in real time. It beats grandmasters at complex games, no problem. Yet a baby possesses this innate ability to just instantly grasp the world through entities and their relationships. A baby knows that if you drop a toy, it falls, and if objects are stacked precariously, they're going to topple over. Generalizing beyond immediate, rigid experiences remains a genuinely formidable challenge for modern AI. Okay, let's dive into this. Here is our roadmap for today. We'll start with the human intelligence gap, then combinatorial generalization. Third, deep learning's blind spot. Fourth, enter graph networks. And finally, the future of reasoning. Part 1, the human intelligence gap, the historical divide in artificial intelligence. To really understand where we need to go, we have to look at the historical tension that has defined this whole field. For decades, AI has been caught in a bit of a tug-of-war. On one side, you have classical AI. This era relied heavily on hand-engineered rules, explicit structures like logic trees, complex grammars. And hey, it was very efficient with data, but it was incredibly rigid. If the world didn't fit the exact rules a programmer wrote down, the system just broke. On the other side, we have modern deep learning. This is the end-to-end approach. It makes minimal prior assumptions, relying instead on massive amounts of cheap computing power and just oceans of data to figure things out on its own. It's incredibly flexible, sure, but it completely lacks inherent structure. It's basically a black box. But here's the thing. The core thesis from these researchers at DeepMind, Google Brain, and MIT is that this is a false choice. Just think about human biology. We use both nature and nurture. We're born with innate, structured constraints, like our brain's wiring naturally looks for objects and faces right out of the gate. That's nature. But we also learn incredibly flexibly from experience. That's nurture. AI shouldn't have to choose between classical structure and modern flexibility. It needs to synthesize both of them. Which brings us to part 2, combinatorial generalization, the power of composition. So the secret sauce of human intelligence is something called combinatorial generalization. I know, it's a dense term, but the concept itself, which traces back to linguists like Humboldt and Chomsky, is beautifully simple. It basically means making infinite use of finite means. Think about language for a second. We have a finite number of words, right? Just a small set of foundational elements. But by productively composing them together using the rules of grammar, we can create a literally limitless number of new sentences, thoughts, and ideas. We construct entirely new inferences from familiar building blocks. And this brilliantly illustrates a point made way back in 1943 by cognitive scientist Kenneth Craik. He wrote that a human mental model has a similar relation structure to that of the process it imitates. Physical reality is built up, apparently, from a few fundamental types of units. I just love that. Craik is telling us that our internal mental models work so well because they actually mirror the compositional structure of the physical world itself. We understand the world specifically because we break it down into distinct entities and the relations between them. Moving right along to part 3, deep learning's blind spots, the hidden assumptions of neural networks. To understand this blind spot, we really need to grasp the concept of inductive biases. Whenever a machine learns, it's essentially searching through millions of possible solutions. An inductive bias is a baked-in assumption, a constraint, that allows the algorithm to prioritize one specific type of solution over another, even before it looks at a single piece of data. For example, if you use a linear least squares model to analyze data, your inductive bias is the assumption that the underlying process generating that data is just a straight line. You're trading some flexibility to get a much more efficient, structured learning process. Now, what's really interesting about this is how it plays out in neural networks. Consider the most common AI building block, the fully connected layer. Here, every single unit is connected to every single unit in the next layer. It's a complete all-to-all relationship. Because every unit interacts independently with no shared rules, its relational inductive bias is actually incredibly weak. It basically assumes absolutely nothing about the structure of the data it's looking at. Compare that to convolutional layers, or CNNs. which you've probably heard are famously used for processing images. GNNs impose a very specific, much stronger bias: locality and spatial translation invariance. They assume that pixels right next to each other are highly related, and that a pattern, let's say the edge of a shape, means the exact same thing whether it's way up in the top left corner of the image or down in the bottom right.
Then we have recurrent layers, or RNNs. These operate over sequences, like processing a sentence word by word. Their baked-in assumption is sequentiality and temporal invariance. They assume that the outcome of a physical sequence of events doesn't just arbitrarily change depending on what time of day it is. The rules stay consistent over time.
So the crucial point is this: standard deep learning components absolutely do have biases. GNNs handle spatial grids beautifully. RNNs handle sequential time steps. But look at the real world for a second. Real-world systems like a solar system or a complex molecule, or even just objects scattered randomly on a table, they don't have a neat linear order or a perfect pixel grid. Standard AI components lack the innate ability to natively handle these arbitrary, unordered relational structures. And that takes us to part 4. Enter graph networks, bridging the gap with structured computations. Let's break down the actual anatomy of a graph network. It perfectly mirrors those human cognitive models we talked about earlier. Entities are represented as nodes. Think of a rubber ball with a specific size and mass. Relations between those entities are represented as edges connecting the nodes. Think of a physical spring connecting two rubber balls, or even a relational concept like is heavier than. Finally, you have global attributes, which represent system-level properties that affect everything, like the underlying gravitational field those rubber balls are bouncing around in. It is literally translating abstract relational math into concrete real-world physics. Because of this genius structure, graph networks can map almost any arbitrary structure in the physical or conceptual world. They don't care about the strict, sequential order of inputs. A graph network can represent the atomic bonds in a water molecule, the physics of a mass spring system, the grammatical parse tree of a sentence, or all the distinct objects sitting on a table in a visual scene graph. It isolates the entities and maps exactly how they relate to one another, period. Let's move on and see how this builds. Because you might be wondering, how does a graph network actually compute this? Well, it does it in a highly structured flow. First, it computes updated edge attributes, meaning it asks, how are the relations or forces changing? Second, it aggregates those edge attributes per node. It gathers up all the incoming influences acting on a specific entity. Third, it computes the updated node attributes. So based on all those influences, how does the entity itself change its state or position? And finally, step 4, it aggregates everything globally to update the entire system's attributes. It's this beautiful, logical progression of thought. Which brings us to our final section, part 5, the future of reasoning, synthesizing structure and flexibility. The massive takeaway from this landmark paper is that we don't need to throw away the last decade of AI progress. By embracing relational inductive biases, specifically through these graph networks, AI does not have to abandon the massive successes and flexible pattern matching of deep learning. Instead, graph networks represent the ultimate synthesis. They're blending the powerful data-driven nurture of modern deep feature learning with the foundational logical nature of classical structure. It's the best of both worlds. We've spent decades trying to teach machines to just recognize patterns. Now we are giving them the structural architecture to understand entities, to understand relationships, and the very composition of our physical reality. If graph networks finally give AI the structure to actually reason about the world the exact same way we do, what limit is exactly left to break? Thank you so much for joining me on this deep dive. Keep learning, and I'll catch you in the next explainer.